Welcome, everyone, to today's Meet the Kavli laureates, and a special welcome and congratulations to our very charming guests. My name is Nancy Basilchuk, and I am a science writer here at NTNU, and
I'm Unni Eikeset, and I'm a science teacher educator, also here at NTNU.
Our first speaker is my boss, Anna Borg, who is rector of NTNU, and she will welcome us and today's guest. Rector Borg, please welcome. Do you want to use the podium?
Helst ikke, men det kan gjøre det. Dear Kavli Prize laureates, President of the Kavli Foundation, sincere friend, President of the Norwegian Academy of Science and Letters, Lise Øvreås, honored guests and good colleagues, and the young for the future. It's a great pleasure for me to welcome you to NTNU and to Trondheim. And first, from me also, congratulations to the 11 Kavli Prize laureates that are present here today. Your scientific achievements are inspiring to us all. The Kavli Prize was established in 2005 and is a partnership between the Norwegian Academy of Science and Letters, the Kavli Foundation, and the Ministry of Education and Research. And they are all represented here today. The Kavli Prize Week is a biannual celebration of excellent science, as well as an opportunity for dialogues on scientific research fields. Today, we will both honor the laureates and have an interesting scientific dialogue. Since 2008, it has been a tradition that the laureates in nanoscience and neuroscience come to Trondheim and NTNU as part of the Kavli Week. In 2020, there was no ceremony due to the pandemic. So this year, we are proud to welcome the Kavli laureates from both 2020 and 2022. Fred Kavli was born in Eresfjord, here in Norway, and he was an engineering student in technical physics here in Trondheim in the 1950s. For this reason, we feel at NTNU that he is a little bit ours. It's also worth mentioning that Fred Kavli became an honorary doctor at NTNU in 2008 and visited us on several occasions until his death in 2013. He left a significant mark through his generous contributions to basic research. The Kavli Foundation has established and supported a total of 20 research institutes entitled Kavli Institutes. One of these is hosted by NTNU, the Kavli Institute for Systems Neuroscience, led by May-Britt Moser and Edvard Moser. We do not have a Kavli Institute for Nanoscience at NTNU, but we have a strong professional environment within nanoscience and a clean room at high international standard. It's undoubtedly many excited and starstruck listeners in this room, me included. I really share the excitement of being here. Again, I would like to welcome you all, and then I will give the floor to the President of the Norwegian Academy of Science and Letters, Professor Lise Øvreås. Please, Lise, the floor is yours.
Thank you, Rector Anneborg, for these very warm welcome words. We are indeed very grateful to you and NTNU, the Norwegian University of Science and Technology, for hosting the symposia in nanoscience and neuroscience since the first Kavli Prize Week arranged in 2008. Your strong research group in both fields adds value to our scientific exchange during the days we are here in Trondheim. As you mentioned, Fred Kavli was studying physics at former NTH, Norwegian Institute of Technology, now NTNU, and he continued his strong ties and collaboration with Norway throughout his life. Upon completing his study, he moved to Canada and then to the United States, where he later founded the Kavli Corporation. And under his leadership, the company became one of the world's largest suppliers of sensors for aeronautical, automotive, and industrial applications. The Kavli Prize honors scientists for breakthrough in astrophysics, nanoscience, and neuroscience, transforming our understanding of the biggest, the smallest, and the most complex. Three fields that Fred Kavli found the most interesting and compelling in our time. Fred Kavli founded these prizes to honor scientists and to recognize outstanding research, while also promoting and celebrating science with the public, inspiring and encouraging their curiosity, support, and appreciation of science. Today, we are following his example, bringing together science, public interested in science, and great scientists, our own Kavli Prize laureates. I very much look forward to learning more of their work and the candidates today. Thank you.
Thank you, Professor Lise Øverås, and thank you, Anne Borg. So, our 2020 Kavli Nanoscience laureates, they have revolutionized the way scientists work across the globe by bringing better focus to an essential tool, the microscope.
But not just any microscope, ones that enable you to see extremely small things like atoms. These are, of course, the transmission electron microscope, or TEM, or TEM, and its closely related sibling, the scanning transmission electron microscope, or STEM. So first, we have a little video in which the laureates themselves will talk about their work. And we can roll them.
I know somebody at Apple in California, at Apple company. And he said, Dr. Rose, without your invention, the iPhone would not have the performance it has nowadays.
The properties of matter, the properties of materials, which are later on used for technology, they are decided in the microstructure. And in the end, it's the interaction of atoms with each other which are responsible for the properties. So when I think our era, the last 20, 30 years, are characterized by going into the small and smallest dimensions in order to tailor materials.
The collaboration between Harold Rosa, Maximilian Haidar and Knut Orban started in earnest in the mid-1980s.
There was a conference in Austria and Salzburg, which we three, Harold Rosa, Knut Orban and myself, attended. And we listened to the talks, and there was one presentation by the Max Planck Institute of Stuttgart where they presented a new microscope they are just purchasing and should be installed in the near future, which is 1.2 MeV microscope going down to, with resolution downwards to about 1 angstrom. But of course, it's a unique instrument, and it's very expensive. And Harald Rose started to complain, just with a fraction of the cost of such a microscope, we could start a project to use a modern microscope, medium voltage microscope with 200 kilovolt, for example, and to compensate the sphere calibration and to have about at least the same resolution with lower energy, which means also able to investigate beam-sensitive materials.
Harald Rose designed in the late 1980s a novel lens design, the Rose corrector, also known as the hexapole corrector, enabling aberration correction in transmission electron microscopy.
I knew the principles. I always was good in mathematics, but without having the physical insight, I never could use the mathematics. If you have to understand that's the problem, and then you know how to go on to make approximations so that you get the result to a few percent, not exactly, but that you can show it will work and how the principle is, and then you can do it in the final design.
Maximilian Haidar realized Harald Rose's idea and designed the hexapole corrector.
What you see here is just a magnetic hexapole element where the electrons then just at the center, which are passing by here in this hole, passing by, and they are reacting due to the hexapole field. And it means that a round electron bundle would be disturbed by a threefold astigmatism. That means we don't have a round bundle anymore, we have then a threefold shape of this electron bundle. And the important point is that one really could see single atoms or interfaces at different devices or different objects. That was really just a breakthrough, and that was actually, I would call it, revolutionary.
The magnification which you can get in this way is up to about 1 million times. Now we have a development towards life science applications of this. It means the most exciting development in the moment is for me that biologists start to use such aberration-corrected instruments in order to advance resolution in molecules. Molecular biology nowadays is close to atomic resolution, but not fully. That means you can, in a molecule, which normally has 10,000s of atoms, you cannot resolve the critical atom.
Andrei Krivanek realized the first quadruple octopole aberration-corrected scanning transmission electron microscope with sub-angstrom resolution.
Essentially, we want to make every single electron that goes through the microscope produce some useful signal. And we can do that nowadays. And so we want to capture the electron, we want to tag its energy, we want to collect a whole bunch of them, and we want to process the images in innovative ways so you can pick up signals that the raw imaging would not give you. Mathematical processing can find out all kinds of signals. Still, it's important to have good optics, so that's where the correctors come in. Our type of microscope makes a tiny little probe and scans it around on the sample. And the probe itself, where it's focused, is actually like typically half the size of an atom, sometimes even smaller than that. To produce the tiny little probe, we can't use round magnetic lenses because they have unavoidable aberrations. This is something that's been known since 1936, and the solutions were proposed in 1948 by a very smart German professor, Otto Scherzer. That's kind of like one of the fathers of this field. And we simply follow one of his recipes. People had been trying for 50 years before it actually worked. So it got a little bit complicated, but if you do it right, it can be made to work. And that's kind of the big advance in microscopy, working aberration correctors.
Please welcome on stage Harald Rose, Maximilian Haidar, Knut Orban, and Andrei Krivanek.
Yeah. over here.
And there's a glass of water here if you need it.
Okay.
All right, pretty cool, huh? Sorry, my enthusiasm.
It's nice to have a video because you can't bring these microscopes here, you know, so it's nice to be able to see it in a video. Yeah.
So, I think we'll start. So we'll start with you, Dr. Rose, since you got the ball rolling, so to speak, by developing the theoretical calculations that would make these microscopes sharper and able to see individual atoms. And that was your doctoral research. And over several decades, you worked on this problem, in the end with your fellow laureates Max Heider and Knut Urban, but you were often stymied by other limitations, such as the stability of the instrument, which I found really interesting. But what I'd really like to know is, what was it like to work on something for so long that you knew was theoretically possible, but so technically hard to implement? What was that like?
Let's put it this way. I ought say to students, I was convinced that aberration correction, because I had the design, and that aberration correction would be possible, but at that time, the stability, the electromagnetic stability, and the mechanical stability which you need. If you want to see single atoms, and you need 10 seconds to make a picture, the atoms must sit in place with accuracy of a few tenths of an angstrom, so nothing is allowed to move. And also the focal length of the lens must be stable, and that was a technical problem which could not be solved by technology available when I made the first design. But so it was just a question of advancement of technology until technology had reached such a performance or a state of performance that all these instabilities could be suppressed to such an extent that you get an atomically resolved image. But you see, then we came in a rather difficult position in 1988 due to the all fruitless efforts made in Chicago and in Darmstadt at the time. So DOE decided, or the experts, so-called in quotation marks, the experts decided that aberration correction by hardware, by correctors, as unthinkable, whatever this is, and can never be realized in practice.
But you proved that wrong.
Yeah, because you see, I say never say never. If there is no
okay, the message from the laureates: never say never.
If there is no physical law which prevents it. For example, there exists one, the second law of thermodynamics, which doesn't allow that we have a perpetuum mobile. Yes, that means the machine which runs without fuel all the time. Yeah.
Yeah.
No, and fortunately, you see then what you showed here in the late 80s, especially technology had advanced to such a state, and what is very important, there were fast computers now available.
Okay, thank you.
So, Dr. Heider, I understand that had your life turned out differently, you might have been an optician, and I'm sure you would have been terrific at it. But how did that make you do this leap into electron microscopy?
Well, I'm not convinced I would become a successful optician because the way how it's working in Germany, at least, as an optician, you have to sell frames and glasses. And then it's much more important the color of the frame, if it fits to the hair or the dress. And I'm not a salesman, and therefore I was interested in the optics as a physicist, but I'm not really in selling frames. And therefore I'm not so convinced.
But how did it help you go into electron microscopy?
Well, I really wanted to continue with physics or with optics, and I started physics in Darmstadt, and then, of course, I could see the Institute of Applied Physics and the Harald Roos was working on. And when I searched for diploma work, I got a tour through the institute, and then, of course, it was clear for me to join Harald Roos's groups to move from eye optician to electron optics.
Yeah. But why did you feel that you had to make a success when you finally succeeded in this?
Was forced to.
You were forced to?
Well, I would call it in this way because I worked at the EMBL. It's a European molecular biology lab as a physicist. And the Director General, when we started the project, he accepted it for structural analysis of biological samples. But then we got a new Director General, and he wanted to get rid of the physicists. And then my contract was not extended anymore, and then was forced because we had to leave. And I wanted to continue this work because we just started this CS corrector project, and then we almost finished it, and we had a successful development of CC-CS corrector for an SEM, for a scanning electron microscope, and a Japanese company approached us if we could develop for them, and then we founded the company with this contract with a Japanese company, with GEO, and since this time we have cooperation, and we have this company since 26 years now.
Wow.
Yeah.
Dr. Urban, you describe building a telescope in your early years as your entry into the world of physics. I find this really fascinating that your interests span looking at things that are very, very large, but super far away, to looking at things that are teeny, weeny, but not that far at all. So why is trying to look at things that are extremely hard to see so interesting to you?
Yeah, I have never thought about this, that these two things are opposite to each other. But I think it's when I built together with my grandfather in his workshop the microscope, it was just that I felt that there is something behind looking at stars. There was, when you're in the age between 10 and 20, there's a lot of movement which is sort of pseudo-religious. You look for something which is secret, which is behind things. And so I was fascinated, and fascination means more than being jealous, it's not only knowing things. You have some internal pressure, some internal passion for that. And I felt similar when I had the chance to enter electron microscopy, because I was always interested also in the history of science, and I knew about the philosophical struggle between Boltzmann and Mach and at the end of the 19th century, where Boltzmann, this in the end quite unhappy person, he insisted on atoms, while Mach, he was the big personality in positivism. He asked him, "Have you ever seen an atom?" Which at that time was, in that sense, making a joke out of these things. So I was aware of this, and now we had the chance, suddenly, to increase the magnification of the electron microscope in such a way that we could probably see these atoms, which were in philosophy since the Greek times.
Yeah, how is it like to be able to then see this thing that they've been quarreling in history about? What is it like?
Yes, I think it's for physicists, it's always important to know there is a lot of history behind that. That's normally not considered so much. But when in order to see atoms, you first of all, you have to ask yourselves, what do you expect when you would see an atom? People are always treating things like this. You spend in the meantime, $5 to $10 million. You buy the microscope, you put something underneath the microscope, as people sometimes say, and then you switch on the beam and there are the atoms, which is not at all so. That means when you switch on the microscope, everything is well adjusted, which takes you a lot of time until things are adjusted, then you see something. Because the electrons, they are not seeing matter as we do it. They react to electric fields. They, in any case, are quantum physical particles. And the atomic world is also the world of quantum physics. So your brain is trained for seeing with light. So no matter what, all the images you get in the electron microscope are first of all patterns which your brain tries to understand with what it has learned throughout its life. So what we have to do is first think about how the quantum physics would give us a signal that there is an atom. For instance, is the atom bright or is it dark? You have to distinguish it from the background. And then when you just look at, you turn knobs. You know, when the common thing between astronomy and microscopy is that you always want to focus. We are really addicted to focusing. That means as soon as you look at something, you have always the feeling, I can focus it a little bit better, and so on. So when you have it under focus, you then see patterns. So you don't know, is this the atom or not? So you have to really explore these things on the basic of quantum physics. You make a model. And then you calculate the conditions which you should adjust in order to see them. And then your model is bad. You have to improve this. And so it takes sometimes days until you really know how to do that. And at the time when we started, this was free territory. People did not know whether the atoms should be dark or bright. And so the first images, they just could not be really understood.
It's amazing to think. It just boggles my mind. And I will say that I was always the student who wanted to focus the microscope, like in biology class, looking at slide. I'd focus, 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 and then I'd drive the piece into the slide and break the slide, which is probably why I'm a journalist. All right. Last but not least, Dr. Krivanek, your piece of this puzzle involves the scanning transmission microscope, although I know you've also worked with conventional TEMs. You wrote in your Kavli biography that at the beginning of the 1990s, there were several ambitious and costly corrector projects that failed to achieve their goals, giving aberration correction an aura of a great idea that will never work. But you and your fellow laureates all persisted, and you, like Dr. Haider, even started a company. So what kept you going? Like, why did you persist?
Well, as Harold pointed out, the equation is very clear. This thing ought to work. So it was a question, why did it not work?
Okay.
And as we kind of gradually discovered, working on aberration correctors,
I think your mic just went out, so it's all right.
So shall we start again?
No, yeah.
So the theory clearly indicated that these correctors ought to work. And as it turned out, in retrospect, when you build an aberration corrector, the situation gets much more complicated. The optics has many, many elements. And you get what we call parasitic aberrations, which are not just a simple focus. It's like how the images start looking elongated in one direction, not in the other. Or you get like Star of Mercedes instead of a clear point. And those in the early aberration correctors would actually make the resolution worse than if you kept the original aberrations. So it was a matter of managing the complexity
And that became much more easy with computers being able to help us. So we knew that kind of background, and people in here in electron optics, we also all worked on spectrometers, where correction of aberrations is very important as well. And the optics in some ways is a little bit less demanding. You don't need to focus things down to the size of one atom. And so we knew from the spectrometers that aberration correction was no problem. We were making spectrometers corrected to third order, and electron microscopy, the third order, was the problem that had not been solved for 50 years. So we said, it won't be that much more complicated.
It's got to be.
And we got into it in 1995 and 1997. We had a working proof of principle aberration corrector. And then 3 years later, we had the best electron microscope in terms of resolution in the world temporarily. This is a race which is like this.
I believe it.
But we got below 1 angstrom with the second generation aberration corrector.
And 1 angstrom, for those of us who are not angstrom literate, how does that compare to the size of an atom?
So atoms have different sizes. The smallest one is hydrogen, and that's roughly 1 angstrom in size.
Okay, so that's pretty teeny.
Most of the atoms, like gold, copper, they sit in lattices 2 angstroms apart. And what keeps them apart is the electrons going around an atom. So the atom, as all the students at the technical university know, is not just one single point. It's basically a nucleus, which is very small, and electrons going around it. And in the conventional phase contrast transmission microscopy, we look at the electrons. So we see the atoms as being like 1 or 2 angstroms large. With the scanning transmission microscope, there's a special contrast mode called high-angle dark-field imaging, and that looks at the nucleus. So that's very small.
Oh my God.
And these days, what we actually see in the images with enough processing is that the nuclei are vibrating. So for the physicists in the audience, there's something called the zero-point motion. Nuclei are not still, they have to vibrate because quantum mechanics says if you put an atom in a certain place, the momentum has to be uncertain, so it has to vibrate. And we are now resolving that kind of vibration.
And
pretty cool.
Dr. Krivonik, I would like to ask you, because I heard that you call electron microscopy the eyes of science. And I wonder, since you've been working so closely with these eyes of science, I wonder how do you look at the atom? Is it like a more physical thing to you than, I guess for most of us, the atom is a really abstract thing that, you know, very, very, abstract.
Or little balls on sticks.
So what is it like for you?
Except the little balls are stationary, and in real life everything moves. And like I was saying, the atom is a cloud of electrons with a kind of miniature solar system, with the sun being the nucleus. And the sun is vibrating like crazy, so it's not actually sitting still. And we can see that in spectroscopy signals as well nowadays. So the world is made of atoms. You know, if you go down to the fundamental level, this microphone is made of a whole bunch of atoms, and that's what gives it the properties. And the first theory about atoms came from the Greeks, and then we were kind of guessing through progress of science that atoms must exist because they explain so many different phenomena, but we had not seen them directly until the 1950s in the field ion microscope. Okay, so those guys were the first. Now, there's a lot of techniques that can see atoms. Electron microscopy is one. Scanning tunneling microscopy is another one. Atomic force microscopy. Okay. So, well, hopefully I'm speaking loud enough. Can people hear me in the back? Yeah, okay.
All right.
Yeah, so no worries. So it's kind of like a kid that gets a whole bunch of Lego bricks. You can build anything out of it, and depending on how you put them together, the models are different. You can do a starship, and you can do a farm with cows grazing in the green field. It's the same thing with the atoms. Depending on how you put them together, you get all the different functionality. Is it going to be the coronavirus, or is it going to be the latest transistor in your iPhone? And so if you want to understand it at the fundamental level, you have to look at the world of atoms. And electron microscopes let you do that. So that slogan, electron microscopy is the eyes of science, that's actually the motto of one of the conferences in the United States. And I should actually issue a couple of little corrections. So the movie that you saw showed me in Berlin. I was doing a sabbatical in Berlin, and the camera crew came down to Berlin to interview me. I'm based in Seattle, Washington State, United States. And one of the things I want to say, so you might get the impression with me being in Berlin and 3 gentlemen from Germany that electron optics aberration correction is 100% a German effort. It's not. Very important work has been done in the United Kingdom, in the United States. Wow.
All right.
First papers we have published in Germany, you mentioned. Just not true.
Okay, we have just under a minute. So this is a flash test. You ready? You have just a minute, one of you, to answer the following question. Can you do it? Okay, Max, you ready? If I could give you magic powers to make something possible in the world of electron microscopy, what would it be?
We could continue.
The clock is counting down.
We could continue the development of electron microscopy, but it's a question of science justification. If higher resolution is needed than, for example, 40 picometers, one can do it, but the efforts are really very high, but one can do it. One can go down to 30 picometers resolution.
Okay.
That would be nice.
That would be pretty impressive. All right.
Well, we have to talk with material scientists if that's needed.
Did you want to say something?
I think in the end, it's asymptotic, and it always depends on how much money you are prepared to spend.
But I have a magic wand. I have a magic wand.
The critical point is you have to convince the people who give you the money that, that your case is such, the scientific case in the end decides it. That means you put a lot of problems together where you really see that having 40 or 30 angstrom picometers resolution would really help you to decide something in materials. And we all know it's not only atoms in that sense that determine the properties of materials. It's the overall action of all these atoms together. That means the scale of the atom is the smallest one. And then you have other scales, mesoscales in that respect, which determine the properties of atoms. So I personally believe that we are more or less at the wake at the beginning of a saturation of the field in that sense.
Oh.
Because the prices go up substantially when you now increase the resolution by another 10 picometers or so. And nevertheless, I think I should make a small correction, which has nothing to do with who invented what. The point is we can measure distances between atoms down to a few picometers. We have talked about much different scales because resolution is one thing, but the actual precision of how you can measure distances between atoms is by nearly an order of magnitude smaller. So when you talk about picometers, this is 1 billionth of a millimeter. Or when you want, I find it much better to say it like this. Take a hair, the width of a hair, in relation to the distance between the Earth and the Moon. And this really, I think, tells you how critical these things are. They are extremely complicated. And this, I think, is just where we feel whether we should explore the properties of matter in these extremely small scales. There's a lot for that, but it's only a part of material science.
I just have to make one observation. I'm fascinated that these gentlemen who work with aberration correction have made corrections to the videos. But your body language, Dr. Kravanek tells me that you have just one little thing to say. We have to watch the clock, but you ready? Go!
I'm not sure about my body language.
Your
I have
microphone.
lots of things to say. And I think, so tomorrow we're all giving 40-minute lectures. So if you're interested in what we were talking about, please come to see the full presentation. We will go in much more detail. I don't think I would want to run out the clock 100%. So.
Yeah, very good.
Have the word back.
A good tip for those of you who want to go into more in depth about their work. Yeah.
Okay, well, thank you, gentlemen. And congratulations again. We'll have you back on stage at the end after Dr. Sagi. Thank you. Okay.
So then you can go have a seat again.
I can take that.
So our next laureate are working at a somewhat bigger scale, but not by much. Instead of atoms, we'll now be learning about smartly assembled layers of molecules. And first, we will have a look at the video where the laureates present their work.
What nature has done for millions of years, I suppose, is assemble molecules, those kinds of molecules which are basic components of fat, called lipids. These kinds of molecules, hydrocarbon-type molecules, assemble naturally in biological substances, in plants. And so it's well known that they can even form thin films, often freestanding films. When we entered the area of pursuing these self-assembly processes, what we did that was different was to cause the molecules to self-assemble on a flat surface of interest. Something nature wouldn't do simply because that flat surface was of no interest in biological processes. Jacob turned to silicon, and Ralph and I, when we started originally, turned to gold. Not purposefully, but discovering by accident that in fact you could self-assemble molecules that on gold surfaces. So the self-assembly itself is nature's trick for millions of years. Our part was to discover it in a new situation that we created. We created the pieces and nature did the rest.
What we've done now is we've said that, the properties that we need are things that can be basically constructed in objects by design. We can manipulate things purposefully as to composition, form, dynamics, etc., and use that beneficially towards particular desired applications. And that's the part of it that I think that's become particularly enabling from a technology perspective. It is possible to affect design at a very high level, and classes of materials which would have been impossible to envision working with in that context. So there's been a lot of evolution. I don't mean to trivialize all the contributions I think go into it, but we started with understanding surfaces and interfaces, and then we based on lots of different contributions went to how to do fabrication and patterning, and and then people were thinking top down, bottom up approaches to doing fabrication, and as you do all that, the footprint gets bigger and bigger all the time, and what would have been an audacious, impossible aspiration, at the outset, actually becomes not that unimaginable as the sophistication of what you're doing just expand in result of the work. SAMS was a start in that process, but it's really gone far and beyond, I think, where we started in 1980, at least where I started in 1980.
Surfaces are so important and so ubiquitous throughout technology and human use that wherever you can find a surface, you can ask a question, which can be scientific or it can be technological. And self-assembled monolayers are helpful to you in understanding that. And I think it's probably that is ultimately the key to use of these things, because what they do is to make it possible to vary the properties of surfaces at command relatively simply. You simply dip the surface that you're interested in a solution containing the molecules that adsorb on the surface, and self-assembly will generate the structure you're interested in. The limits to self-assembled monolayers are that most of the molecules that are used right now are
pretty simple molecules. Now, you can make more complicated ones, but when you make more complicated ones, then the technology becomes more complicated. And one of the virtues is that we, in particular, really believe as a principle of doing research that to make good science into good technology, it's easiest if everything is very simple. So there's a lot to be said for just thinking about simplicity as a guiding principle in research. And if you're trying to make something that's modifies surface properties at 2,000 degrees, or you're trying to make surfaces that are amenable to extreme X-ray exposures or whatever, that's hard to do, and that's going to require more work.
I claim that our research, what we are doing, is leading itself. What I mean, you start with something, eventually discovered something that you didn't think about. I mean, you had some idea, but not necessarily what came out of it. And this leads you to the next step. And then again, it can go in different directions. So actually, the research leads itself if you have an open mind. The best thing that can happen is that something doesn't work according to your original idea. Good things come out of this, what is called serendipity. But you have to have a prepared mind, and of course, if you don't work on something, you cannot discover. You have to work on something that may lead you to the discovery. But you cannot plan the discovery. But once it's there, you have to recognize it. And then you have to work hard to prove that what you think is there, it's indeed there. And it's not a fake. All this is a game, actually. You have to let people playing, you know. There are different kinds of science. You can work for a certain purpose, to make a certain device, you know, applied science. And this is okay, it's fine. And you get also satisfaction if you manage to do something useful. But to discover something new or to come across something you didn't expect is very exciting. So we are actually, I think that all my life I was playing science. And this was more or less a hobby. The work was only how to get the means to do the hobby.
I think forward-looking, I think the applications in biomedical contexts are really quite interesting, and they're the ones that I'm most interested in at this point in time. When you start working with living things, you know, the first thing you have to come to understand is they do have, you know, a mind of their own. And almost everything that you can do, you know, to perturb a system, you know, perturbs the system. It's very complex.
Please welcome on stage Jakob Sargiv, Ralph Nutso, representing.
So welcome, Dr. Sargiv, and unfortunately Ralph Nutso couldn't be here, and not Alara or Whitesides either, but I guess you know them, so you'll help us also understand.
You have to do everything now.
So we heard in the video here that nature already builds these monolayers on surfaces. But I'm really intrigued in, okay, so if I have a flat surface here now, why is it interesting to be able to build a layer of molecules on top of this?
Okay. So as I'm a chemist, we are talking now about, you know, nanoscience is an extremely broad field because it implies small things. Small things can be approached from different perspectives. You may be a physicist, you may be a chemist. We are chemists. These are monolayers or single layers of molecules made of organic molecules. Now, why is this interesting? All materials terminate with a surface, or more precisely, we are talking about interfaces. Unless you are in vacuum, then you always have a boundary between a solid and a gas phase, for example, air, or with a liquid. And the surface is the site where a lot of action takes place, because this is where molecules can stick to the surface. It means they can adsorb. And there are many processes of adsorption. One of them is what we are using is along with the molecules that have the capability to form a structure, and then you obtain a single layer of molecules. Now, this single layer of molecules may transform completely the properties of the surface, and the surface itself influences the underneath what we call the bulk of the material. So what happens of the surface is extremely important. You all are familiar with Teflon dishes to which water doesn't stick, and also oil. When the dish is fresh, is new, you put oil, it goes away. So with our single layer of molecules, we can, for example, coat a surface, which may be a metal or a glass or gold, as we heard. Gold is also a metal, a particular metal. So, and then a surface that when it is clean, I say clean because usually the surfaces are not clean, they are dirty. What does it mean they are dirty? Some molecules from the air or from a liquid anyhow stick to the surface, but this is some undefined coating. And a clean surface, for example, a clean glass surface is not wetted by water. It is so-called hydrophilic. When it's dirty, it becomes oily, so the water can go away, but not very well. When we put our monolayer, it's like Teflon. So the water wouldn't stick, the oils would not stick. So it is hydrophobic, we say. Hydrophobic hates water.
Hates water, yeah.
And it is oleophobic. It hates oil. And what is interesting that these layers are formed from a solution in which the solvent, which is the oil, would wet the surface. Once you put the active ingredient, those molecules that self-assemble, that form by themselves by spontaneous adsorption, this well-defined monolayer, the surface is no longer wetted by the solution from which it forms, so you call it autophobic. And you can watch with your eyes the formation of such a layer. You can take a piece of glass, for example, and it should be clean, because if it is not clean, it's dirty, it is coated with something else which is undefined. Now, to make a clean surface, these gentlemen of the microscopy know that is very difficult. Okay. So, but usually it is made in vacuum. But to keep it clean in air is very difficult also. So, to make a really hydrophilic surface, we cannot keep it in air. We have to keep it underwater, and the water must be extremely pure. And once you take it out and you put in this, you have to dry it, and you saw in that movie that with a jet, yeah. Yes, with a jet of clean nitrogen, which is drawn from liquid nitrogen to be really clean, not just nitrogen. Then you work extremely rapidly in a clean atmosphere. You saw also a clean hood, which is actually a biological hood, which is a laminar hood. So the hood must be clean, the liquid must be clean, everything must be clean. You put it in the oily solution, the organic solution containing these molecules that form the layer. And without the active component, it will come out, the solid surface, let's say glass slide, will come out wet with a thin layer of liquid sticking to it. Once you put the molecules that form this monolayer, and it may take seconds to a few minutes, hop, you come out, the surface come out totally clean, the liquid doesn't stick to it. And this is very important property, because you have first the self-assembly, it means the molecules know how to build this, but then you have to prevent more material to stick with it. If more material sticks, you are not going to have a single monolayer. So it must be autophobic. It means once it forms, automatically switches off further adsorption to the surface. So then it comes out completely clean. This is you see with your eyes. Now you have to prove that it's a single layer of molecules. This is much more complicated.
Maybe that's where the microscope comes in.
This is the next question, of course.
It sounds like I could use some of these self-assembling monolayers in my house.
You can use, actually, I coated my windshield with such a layer of molecules, and I drove from Rehovot, our city is about 60 kilometers away from Jerusalem. Jerusalem is on the mountain, it's 800 meters. On the way, there was a heavy rain, Probably like here in Israel, not so. We don't have rain in summertime, but in wintertime. And I didn't need any...
windshield wipers?
No, I was the only one driving fast because the windshield was hydrophobic, and the faster I went, the better it was. The water just
Okay. How do we get this?
Yeah, we need this here in Norway.
What did you put on? What molecules did you?
A single layer of molecules is called. This is the hero I'm going to talk tomorrow. Yeah. I'm going to think about a single monorail, the life of that monorail from the minute I started. I used it for the first time in 1978 until these days. It is going to become a big hero. So I should advertise for tomorrow.
Yeah, come tomorrow.
So the title of my lecture tomorrow is The Exciting Life of a Most Boring Monolayer. Why it's boring? This monorail, all it could done is what I just said. It sheds water, it sheds oils, and it's a very good ultra-thin electrical insulator. Okay. It has been used and by many groups. We did these first experiments to prove electron tunneling through a thin barrier. The thickness is about 2.5 nanometers. So it's an extremely good electrical insulator. So it is an insulator. It means it prevents electricity from flowing. It is phobic, and that's it. And what you can do with it? You cannot do with it anything else, so it's boring. And now we know how to convert it locally into an extremely high conductor, apparently, perhaps superconductor at room temperature.
Oh, I guess we'll have to...
So come tomorrow, it's going to be exciting.
That's a pretty exciting invitation. So we have time for one little question, and I get to ask it. So now after seeing this video, I know that you're a very playful person.
What do you mean playful? I play science.
Yeah, you play science.
Yeah.
But I also understand that when you were a kid, you almost set fire to your house because you were working with an experiment with gunpowder.
Yeah.
So this is true, right?
Of course.
So how does that... You talked a little bit about this, but can you tell us how that experience and your childhood interest has influenced your choice of career?
Okay, today is not dangerous. You heard that you have escape. I carry with me no gunpowder. Okay. Look, I got interested in science at the moment I started getting lessons of science, and this was in the 5th grade, I guess. By the way, I was born in Europe, in Romania. So it was under the communist regime, and there were many bad things. Science was very good, and the science teaching was very good. So in that environment, it was useless to be attracted by humanistics because all was fake under the communist regime. So science was the only really discipline that was true. So the truth was in science, you know. You could express your truth, otherwise everything was nonsense. So as a kid, I was attracted by science from the first moment. So my first experiment was also actually distillation, which I built an apparatus.
Yeah, dry distillation of wood.
Yes, it was in the 5th grade. I did dry distillation of wood to get some methylic alcohol. No, this is not for drinking. This is a poison. This was methylic alcohol. Okay, but then when you evolve, of course, you want to do exciting things. And what is exciting? Exciting is you get some explosive, you know. We learned what is gunpowder, and there are also if you learn a history of science, you know, the father of modern chemistry, Lavoisier, who actually he didn't discover oxygen, but Priestley discovered oxygen. At that time, they said fresh air. They didn't know what is oxygen. They say fresh air. Lavoisier was the first to show that what is oxygen that is needed for burning and is for oxidation, also for life. But Lavoisier was also working on gunpowder, and he perfected it, and this helped Napoleon in his wars because he had very good quality. Lavoisier, I mean, the time he worked was before the French Revolution, because unfortunately at the French Revolution they removed his head with the guillotine. For other reasons, not for discovering oxygen, so don't be afraid.
Don't be afraid.
What did this have to do with your gunpowder?
Okay, so then you read all this.
We need to know about the gunpowder.
Okay,
part.
so then you want to do something that is you know, exciting.
Explosive.
Okay, and I had a friend who started playing with this, and he said it exploded to him. I said, okay, because you don't know how to do it. So I did it and also exploded, because I tried to mix them, you know, and then you create some friction, and it's just one grain that you push, and then poof, it explodes. But I used this gunpowder. You know, there are so-called Chinese arrows. The Chinese actually invented the gunpowder, and they used arrows on which they put a small tube with gunpowder, and when you shoot the arrow, you also ignite the gunpowder, and this becomes a small rocket. Wow. And then the arrow can fly further, and actually made such rockets.
You made those?
Yes, yes. I even launched my physics teacher. We would get higher marks if we show some applications of physics. And I told her that I know how to make these rockets. Then she said, the teacher, please bring it to the class or show us. I said, I cannot launch it from the class because it makes a lot of, you know,
sparks.
Yes, yeah. No, and
fire?
The fire and gas. I said, no. We open the window and it flies through the window. So when I did it, it actually flew out of the window, but all kids went out from the class because it was full of smoke, you know, and all this. So, and then I didn't get the high grade because she also went out and she didn't manage to put it in the right place. So this is the kind, you know, the things that a kid is doing. But as I said, it exploded in my home, and the carpet took fire. And then my father said, look, I know that scientists also sacrifice themselves for the sake of science, but I don't think it's worth doing it for something that was already discovered.
Wow. Well, with that, I think we'll say thank you very much.
Yes. And please,
all right, stay here.
So, now I would like to invite also the 2020 laureates in nanoscience to the stage, and then we'll have a joint discussion here.
Yeah, so
we'll have to make room for all of you.
Does everybody have their microphone still on?
Yep.
If not, you're in deep trouble.
It's on.
It's not. No, it is.
Is it?
Can you all hear?
I don't know. Hello?
Yep. Please just get thumbs up. All right. Have a seat. Do we have enough seats for everybody?
It doesn't work. I'll need the hand.
No, it does. It does. Yeah, they can hear you. You can hear Andre. Yep. All right. Excellent. All right. So this is the chance for all of these eager students in the audience to participate by asking questions. I know it's a little intimidating, but you can see these guys are super friendly. I mean, they're blowing their houses up. What's to be afraid of? And as Dr. Rose said to me, there is no such thing as a stupid question. So is there anyone who has a question now they'd like to ask? If not, we can ask our questions, and then you can build up your bravery.
We can start out, and then you'll just have to think about a question, and then we can allow some questions.
And we have someone who will run around with a microphone. If you have a question, if you're feeling...
May I ask a question?
Yes.
Yes.
You are talking about size of atom.
Yes.
How do you define it? Quantum mechanically, I think there is no boundary, sharp boundary to an atom. How is the size of the atom defined? I mean, the electron cloud is not something with a sharp boundary.
No, but, sorry, I came just by, you measure the scattering. Yeah? Then you find the size. It's just because an atom consists of a positive nucleus and then all the electrons around.
But they are not, you don't have a sharp boundary there.
No,
Yeah,
you don't. No,
it depends on the experiment you are doing with it.
No, good.
Yeah, when you measure the size, you do an experiment with this particle or with your layer or so with the atomic force microscope.
Yeah.
And so you just shoot, for instance, an electron on it, and then it's an acting diameter, and this is what you take as the diameter.
But you, Dr. Krvanek, you also use this scanning electron microscopes, and then, like you have said, that you can ask atoms questions and get answers with that.
So we get spectra, and spectra are full of information. So they tell you what type of an atom it is. They tell you how they're vibrating if you have sufficient energy resolution. And they can also tell you about what kind of an environment they sit in. So they can tell you about what are the near neighbor atoms. That's all be done experimentally. Come to the talk tomorrow. I'll explain how it's done.
But
can I just say one thing? So, but atoms are a physical reality. So we could get into philosophical discussions, but I believe they exist even when we're not looking at them. And a very interesting statement from 1948 by Denis Gabor, who's known for holography. He said, when electron microscopy gets to half an angstrom resolution, it may have to stop there due to lack of objects. So he didn't have the resolution, but he knew his physics. And basically, the smallest entity that we can resolve is the nucleus. And the nucleus is vibrating on a scale of about half an angstrom. So if we have 0.1 of an angstrom resolution, we won't see anything extra than we see already now. So we pushed it to that boundary.
But can we ask you, is there any cross-fertilization between the two topics that you're working on here? So can you use these type of electron microscopes on your monolayers?
We are talking as chemists, we have two connected tasks. One is to make molecules or molecular structures. The other one is to find out what is that. This is synthesis and analysis. And when you come to structures, for analysis and structures beyond the molecule, you need microscopes. So without microscopes, you don't know what we are doing. In what we are doing right now, we have not yet used electron microscopy because with electrons, we also modify our molecules. And then the measurement modifies the measurable. This is one problem in general in science, because any measurement, if you go down to the nanoscale, modifies something. So for that reason, we use microscopes, but we use atomic force microscopes, which are not based on electrons. I presume that we should be able to use electron microscopes, which may have higher, of course, they have higher resolution today than atomic force microscopes. But we have to find the right conditions. And this is additional work. Now we are a very small group, and we have to decide at each moment what we are going to do next day, whether we concentrate on this, on that, and there are many tasks and little money. I mean, money is connected to the size of the group you have, how many people you have, and what are the tasks to do. Yeah. But I guess that it should be possible, and we should start looking into this direction of using the electron microscope.
Yeah,
because with an atom force microscope, you also interact with the object. You're also modifying the molecule.
No, depending. No, you can use, depending how, of course, you can write to it, you can scratch the surface, but there are many other problems there, the resolution, because you use a tip, and the tip has a size which is much bigger than an atom, of course, so you cannot actually...
And also the distance. So the fewer interaction you have, the worse is your resolution.
You are rely on forces.
If you want to come closer, create a finer and finer resolution, you need stronger and stronger interaction.
So this is a general problem in nanoscience. What you measure, what you see, this is what you are talking about. Yeah. What you see is not exactly what is there. And you have to interpret.
No information.
Yeah. But how, when you, okay, so now we've heard how Dr. Sagiv uses microscopes, not necessarily your type of microscopes, but when you're working on resolution, how do you decide what to use? Would you use a self-assembling? You probably wouldn't use a self-assembling monolayer, but you're working with a tool. So how do you find the object upon which you will perfect your tool?
Yeah.
Got that?
The word upon is the point.
What's that?
You know, we are always talking about these molecules, but we are not talking about the structure of the surface where he puts his molecules on. And this we can investigate by electron microscopy. There is a lot of work done in the moment to really find every atomic position on a surface on which you then put your molecules. So this works quite well, and as I said, it's one of the hottest topics in the moment in electron microscopy science. And there you measure the distances with this high precision, which I have talked about, the hair to the distance of the moon from the Earth, and then you can calculate, because that's always the point. Physics needs calculation. To see atoms is an aesthetic category. I like to look at things from aesthetic points, but then in the end, we have to come to numbers, because only the numbers in the end make you or give you the access to something you can use. And so the surfaces can be calculated, and we can really measure atom by atom the positions of the atoms on the surface, and then your wonderful molecules come.
Okay.
And,
but can we just see? Is there a question in the audience?
Hopefully.
Yeah.
All right.
We do have one.
Who's the microphone
There's
runner?
coming a guy with a microphone here.
Well, this attempt.
Hello, can you hear me?
Yes, very good.
Perfect. Hello, my name is Eleanor, and I study nanotechnology here at NTNU. And first, I must say, I find it extremely refreshing and fun to hear 4 scientists being asked about if you got magic, what would you make out of it? And everyone was like, we don't need magic, we need money. And that's amazing to hear. So the question must be then, if you had unlimited supplies of money, what would be the biggest step in your research possible for you to imagine? Because we are talking about seeing atoms. So when I ask about a big step, I do not ask about like slightly better resolution. What is the next big step for your electron microscope and your monolayers if you had unlimited supply of money?
Very good question.
Yeah, do you want to start, Dr. Krivonik?
Sure.
So, we're quarreling.
Oh no, dueling!
Yeah.
Okay.
Let's start with Dr. Rose.
Okay, all right. I guess we're going to start with Dr. Rose. I saw you fidgeting in your seat, so I thought.
If I would have unlimited funds, and what I say, then I would try to get a team of experts. And what would be our goal? My goal would be to make tomography on organic substance, in like a gene or something, and then you have to go to a liquid helium in order to reduce radiation damage, and then do like tomography. You know, if you have some, for example, if you have a tumor in your brain, then you get a tomogram that they can exactly locate it where it is. Right now, we are talking just to get images of surface of 2 dimensions. But what really is interesting, how does its atomic structure in a 3-dimensional object?
Wow.
And say you need much higher resolution, much better microscopes, and also the problem, let's say you want to have organic material, then how can I reduce radiation damage? So that each biological object can tolerate a certain dose, and then it's a question, what can I do to get most information with the dose the object just just can tolerate. And I think this is the way to go in future. And it would be so important, you see, for medicine and for cancer research and everything. So perhaps then we can find a cure. I think this money would be wisely invested.
Should we go, maybe take Dr. Krvanek next, and then you ready?
Oh, sure. Yeah.
Unlimited funds.
So electrons have the wonderful property that they interact with matter extremely strongly. So you can have one atom, you illuminate it with a beam of electrons, you get all kinds of signals. If you illuminate it with optical light, one atom is not going to produce any significant signal. You will need millions of them. And that wonderful property comes with a big disadvantage, is that that strong interaction can knock the atoms about. So, for instance, Jacob's wonderful molecules, the hydrogen in them, if we illuminate it with electron beam, as soon as we put something like 10 electrons per square angstroms, the hydrogen is going to start disappearing. Yeah. So a miniature explosion in your sample that you may not want, and you basically destroy the structure as fast as you're examining it. So if I could have one wish, which is not physical at all, it would be, could we please keep the interaction that gives us the information and remove the interaction that destroys the sample?
Wow.
It depends on money or what?
Physics doesn't allow us to do that. So we're finding ways around it. And for instance, I think everybody in the audience has seen a picture of a coronavirus. That came from an electron microscope. And the way it was obtained is that the electron irradiation on individual viruses was kept at an extremely low level. Yeah. The result was that the individual images were very noisy. Just imagine the worst TV image that you've ever seen. You can't make out the face of the person at all. That is the quality of images that electron microscopy works with. But the advantage of viruses is you can get 1 million copies of identical virus. So you take 1 million images, you combine them all together, you get a beautiful three-dimensional image. So that's one way to get around the radiation damage. Another way is if you don't have hydrogen around, things like carbon will stay in the structure as long as you lower the energy of the primary beam. So one advantage of aberration correction is that we can get good spatial resolution with low energy beams, and we go down to like 40 kilovolts, which is much lower than where we were with microscopy 10 years ago. And we can just sit on that one atom, send 10 million electrons past it, and it will stay there. And that's when we're interrogating them and saying, what kind of an atom are you? If it disappears after 2 electrons, we never find an answer. Okay, so radiation damage is the big problem in electron microscopy, and there are ways around it. Another one is when we do vibrational spectroscopy, we don't actually have to illuminate the sample directly. We can park the beam just outside it, and we limit the energy of the interaction. So we keep the useful signal, and we avoid doing radiation damage. So
cool.
That's very exciting too.
But as soon as you have interaction with the object, you're modifying the object, and therefore you have radiation damage.
You can choose the energy of the interaction to limit it, as we do in the spectroscopy.
But for example, 40 kilovolt electron microscopes already existing. They have sub-angstrom resolution, as you know, in Ulm. At the same time, with tomography, I think it will come, not far in the future, that you can do optical sectioning with an opening angle for the stem mode, for example, of 100 milliradians. And then you can really go down with a C resolution to about 2-3 angstrom in the depth resolution.
In thin sections.
Exactly,
and then put the picture together.
And then you have tomography, and then you don't have to tilt the specimen. You have all the information. But of course, just the image and not yet spectroscopy. Spectroscopy, it's a different issue, and you also can work on this one, of course, yes.
Let's hear about what do you think, Dr. Sage, giving unlimited results? What could you do?
The amount of money would be a disaster. Imagine that you are a hungry human being and you have no money to buy food. So you need money to eat something. No. But if you have an unlimited amount of food, you may get obese. It's not good in your health. Now, if we have too much money, we are thinking what to do with the money. We are not thinking about science. So there are so many things I would like to do. So if I would have unlimited amount of money, I don't know what to do first. What to choose. So lack of money stimulates our mind.
Exactly.
The problem, if you don't have enough, you have to have the right amount of money. If you have too much, it's not good. If you have less, then you badly need to do something, is not good.
No.
And we are talking about this situation, not that we need infinite amount of money. This may not be good.
But that brings me over to the question of funding. So, because as laureates, yours are stories of success, but I guess you all must have experienced some difficulties and setbacks, like, for instance, lack of funding. So do you have any perhaps there's some coming scientists, the researchers sitting here, do you have any advice to them on
Yeah, why don't we start with Dr. Urban?
So I think our example is not, it's a typical example, but it's not really advice. Because in our case, there was a comment on the 50 years, I think this was you. You know, when you have worked for 50 years, one doctor student time is maybe 3 to 4 years. 50 years, so that's many 10 students who have worked on this worldwide for 50 years. I think as a politician, you should decide to stop that work. Because that's, you know, that's an enormous amount of money for 50 years, for many 10 of people, for hundreds of people. So this, for human circumstances, tells you that this problem is, in the moment, not solvable. I think we should not always shout on the politicians and say you made a mistake, that you didn't trust me, because there are always others who also come with wonderful proposals. And so when the money flows into electron optics, and nothing comes out, I think it's natural that you become skeptical. So I have talked to politicians quite often, and I think they are under a condition where they have not infinite amount of money, but very little money, which they have to give to the right proposal. So in our case, we had the decision not to fund this anymore. And in our case, there was a young person at the Volkswagen Foundation, and he trusted us, and he more or less guided us through the procedures in a positive way. Normally, funding agencies, they try to discourage you and so on. But he helped us to advance. And then in the end, the majority of the committee was just a single vote. So we worked hard on the people, giving lectures, advertising, on conferences, and so on. And we worked very hard, and then we had a single vote majority. And that decided the things.
So you need someone to support you. That's
right. And I think afterwards, it's always, you know, Thomas S. Kuhn, this philosopher and the historian of science, he said, this is a paradigm change. Paradigm change means more than 100% change in things. So after a paradigm change, the world cannot be thought back. It's very difficult for you to think about a world where a certain thing which is now determining your life was not there. And in that time, we had also enemies. So at the time when we started to do our first studies in the new microscopes, I received a letter from one of our big heroes in electron microscopy. And he blamed me and said, this microscope, aberration correction, is in itself an aberration with respect to financial points. And so he said, we can live without aberration correction. Oh. And so I still keep that letter because it is clear a real paradigm change needs new thinking. And this was exactly in that moment. He really did what makes it a real paradigm change. He said, you are seducing the people to spend these enormous amounts of money, because nowadays 10 to 15 millions of dollars or euros are flowing into these instruments.
Well, so I guess we will take out of this that you need to really believe in your own idea and just go for it, and perhaps also try to find some good
be in resonance
support
with those who give you the money.
Yeah.
If you just postulate, I'm the greatest, I need the money, there's never enough money. And I think you made the right remark. You didn't talk about infinite money. You only wanted to say if you would have a lot of money to do something with this, then I personally would...
I'm sorry, we're out of time, but so we would like to thank all of the laureates for coming, and thank you to all of you in the audience.